Couple of lectures I've talked to you about magmatic compositions, and I've talked about the magmagenesis techniques that are required in order to get the geotherm to cross the solidus by plus T minus P and plus H2O mechanisms. Today in Magmas number 3, which by the way is chapter 4 in our textbook, which is opengeology.org. There's good textbooks there for a lot of different geology topics. Excuse me for clearing my throat. We're going to do 2 lists, and the first list today is magmas in the crust. We talk about them sitting in magma chambers. Well, let's go beyond that level. And so our very first point within this is going to be, what is a magma chamber? We call it in our community a pluton. Now, we actually still, that's a O. So pluton, and a pluton is a magma chamber. It's a single thing, largely. It's a balloon. We could also sometimes call it the reservoir. In fact, we prefer in the science to call them magma reservoirs more than even magma chambers, because chamber sounds like this big echo chamber. These can either be molten or they can just be preserved at the surface as rock. So let's say these are either molten in subsurface, or exposed at surface as a rock, and it's been brought to the surface by erosion or faulting. We call that process exhumation. Let me show you an example of an exhumed, it's probably the most beautiful picture I've ever seen of a pluton, of a single magma chamber. And this is from Patagonia in South America. And what we see in this picture is a white rock, this whole area that's white. And it's been cut through by glaciers, but it is a magma chamber. And the roof of the magma chamber is here in the red line. It would have come across like so, and here it would have, and the floor of the magma chamber would have been somewhere down here. And so all this material, the beautiful Patagonia mountains, at one time was a magma chamber, a pluton. Now, when many times in these different environments that make magmas, subduction zones, volcanic arcs, there can be pluton and pluton and pluton and pluton. And so this there has to be a word for a cluster of plutons, and we have one. It is batholith. So if you ever hear about a batholith, we're talking about hundreds of kilometers worth of pluton stacked upon pluton stacked upon pluton. Below the Cascades or the Andes Mountains, Central America or Japan, where there are active volcanoes, you might expect there to be dozens, if not hundreds of plutons from the last 1,000 to million years. And all those together would be called a batholith. Now, how does magma then move through the lithosphere? How does it move from pluton to the Earth's surface? Well, it does it through conduits. So here we go in number 2. Our second in this list is we're going to call these things magma pathways or magma conduits. And there's 2 different types of these feeder systems or movement systems, and it depends on their shape. If the shape is inclined, all right, so it's vertical or sort of vertical, we call that conduit a dike. And if that conduit is closer to horizontal, it doesn't have to be perfectly horizontal, but if it's closer to horizontal, we call that a sill. And you can think of these as pipes, but maybe better than pipes would be a sheet, a tabular sheet. Of course, we do have sometimes where there are volcanic pipes, but it's best to think of these features as tabular sheets, cracks that open up that allow the magma to move through them. If we were to sketch this where it occurs relative to a volcano, we could say that there's a conduit that connects down to a pluton. There's our pluton. And this pathway that is vertical is our dike. But if we had any units shooting off the side, then those things would be called sills. And these are actually very common. So let me show you a couple pictures in real life of dikes and sills. The first example is from Iceland. The second example is from Antarctica. These are some of the best pictures I've been able to find. And what we have in these pictures is a series of sedimentary rocks. And our dike is moving up in this direction, opening up a pathway as it tries to reach the Earth's surface. And then in this other picture from Antarctica, we've got some features. All right, so here's our host rock. It's our country rock. And then there are dikes in black that are cutting across it. And then there's even maybe this one in white is a dike, or maybe that's a sill. We're getting into the gray area. And then here, maybe this would be considered a sill. So those are our two different types of magma bodies, how those exist. And now for the last lecture bit on magmas, I want to talk about how you can change a magma composition. And we're going to do a list here of 3. How do you change magma composition? From a basalt to a rhyolite, or from an andesite to a basalt. You can go in various directions, but most of the time the pathway is towards more felsic. And the Earth operates in 3 main ways to do this. The first way actually violates what I just said about the pathway towards more felsic. So maybe I shouldn't have had this one first, but it's the easiest to visualize, and that is magma mixing. With magma mixing, you create a hybrid when 2 magmas meet. Create a hybrid when 2 magmas meet. A picture of this and a schematic of this is illustrated here. We actually have a pumice that shows magma type 1 and magma type 2 before they were able to fully hybridize into a single thing. And in this picture, I like how we have this magma chamber B opening up a dike and mixing into magma chamber A. Oftentimes magma chamber B, the one that's doing the mixing, is mafic because it's coming up from below and because it's lower viscosity. Right? Lower viscosity means able to flow better. So in this case, a magma mixing would make something more mafic. In fact, we know what we should do? Pathway is towards more felsic. Let's erase that. Bad teaching. It can be that, but clearly there's other things too. All right, our second process is called assimilation. Assimilation is kind of like mixing, except for it's not the mixing of 2 magmas. It's the incorporation of a solid into a magma. And so we could, let's say this as our definition, magmas melt and incorporate local, or ingest, I like that better. Magmas melt and ingest local rocks. The country rocks that are surrounding that magma chamber are being exposed to very incredible amounts of heat, and they can break off and sink down into the magma where they're not stable. They're going to start to melt. And so in this example, what we have are some chunks of the local country rock here in Texas. It's a metamorphic rock. And they're in a host of granite. And so as that granite sits around this and warms up these chunks of country rock, it'll start to melt them. I guess a really good example of how assimilation could change composition would be remember limestone? Let's say a magma chamber is sitting within limestone, which is made of calcite, which has a chemical formula of CaCO3. And so if you were to ingest tons of calcite into a magma, what you would be doing is the magma would add these components, Ca and CO3. So it would add CaO plus CO2. That is assimilation. Now, on our third mechanism, it's called fractional crystallization. That's number 3. Fractional crystallize. Fractional crystallization, and fractional means progressive. So it's this progressive removal of crystals that change the composition of the melt. Let's just go ahead and do that. So we're going to say progressive removal of elements by crystals. Those crystals sink to the bottom of the pluton, or they rise to the top. And by doing that, they get isolated away. All right, so here we go. And here's our magma chamber. And so what we're saying is there are crystals that are forming, and they soak up some silicon, some potassium, some sodium, and then they sink to the bottom. And here's another one, and it sinks to the bottom. And then the residual melt changes its composition because it's lost, let's say in this example, sodium from both of those crystals. Well, then the melt that's remaining is going to be less rich in sodium. This is the process that tends to go towards felsic. And we're actually going to do an example of this. It's kind of mathy, but let's imagine we have a magma reservoir that has a bunch of basalt. That is the liquid inside. And that basalt, mafic magma, it has inside of it 15 weight percent MgO, and it has 45% SiO2, and let's say it has 40% everything else. We'll say else. And we subtract from that basalt a bunch of crystals, and those crystals are olivine. And the composition of olivine is 50% weight percent, 50 weight percent MgO and 50 weight percent SiO2. The residual magma is going to be depleted in whatever the olivine soaks up as a sponge. In this case, the biggest difference, right, is going to be the MgO. So our residual magma, we would then have to expect is that it's going to be lower in MgO. Silica is actually pretty similar, right? 45 to 50. So we can't really speak too much to that, but we certainly can see how the olivine is the sponge that soaks up the magnesium. What's kind of cool is that sometimes this process is recorded in crystals. And we're going to say sometimes recorded in crystal growth rings or patterns. And what I mean is it's kind of like tree rings, where sometimes a crystal will grow and it preserves these really delicate layers inside of it that represent earlier episodes of growth. And in the middle, it might be super mafic. And then by the outside, the composition is felsic because it's recording this process of fractional crystallization.